Okay, so let's go. Practicing unsafe stacks. So very happy with the name. So how using the unsafe package in Go can reduce allocations occasionally with hilarious consequences. So disclaimers, I'm by no means an expert in writing low allocation code. I've only recently went down this journey of like researching how it can be done. I'm by no means an expert in memory safety, which is why I use a language like Go, so I don't have to think about that. And I am by no means advocating you do a single thing I show you today, because like we completely off the rails at certain points here. So what is unsafe? So just to start here, just as a bit of a preamble, if you're new to Go or you're new to programming or you're intermediate in Go and intermediate in programming, the things I'm going to show you here today don't necessarily need to be known. How would you put it? Unsafe can like completely subvert the Golang type system. And whenever I wrote the first draft of this presentation, I was like really nervous that I made it sound easy and fun to use whenever it's actually is quite dangerous. So for this, I kind of think that if you're going to use this package, you need to have like a reasonable understanding of what exactly is happening under the hood. So we will be talking about memory and we will be talking about how Go structures its data structures in RAM. But don't worry about that if it scares you. You don't need to know it whenever you're doing general day-to-day Go. I wouldn't even say seniors and principals have to touch on this information. It's just bonus fact. So what is unsafe? A pointer in Golang has an associated type and points to some address in memory. Using unsafe, we can point to some address in memory, but without an associated type. We can then later cast a type to this pointer. So a quick, that's already went through that morning. So as of Go 120, unsafe exposes the following. It exposes a function of offset off, align off, and size off, which we will quickly brief over because they're not really important for this. But then it has a func for string, string data, slice, and slice data. So string and slice both create a new string and a new slice in ways we will see later on incredibly quickly. String data will return the pointer to the first character of that string. Slice data will return a pointer to the first element of that slice. Arbitrary type is just Go's like previous way of like writing, I don't know, code that's untyped before generics came in. I think like it's an int under the hood, but you can pass anything into this. We have a pointer and we have an add function for pointer arithmetic in a slightly safe way, but we'll just quickly get into this these quick three functions. So offset off returns the offset of how far into a memory a field in a struct is offset in that struct itself. So if I do offset off this anonymous struct here, I can't highlight that here. With name in this anonymous struct, we get an output of 8, and this is due to struct alignment, which isn't in the scope of this. But if we kind of rejig it a bit, and then we add a bunch more fields to registered, holy hell, oh wow, then a byte of 2 flags, the offset of name is still 8 because 1, 2, 3, 4, 5, 6, 7, and then the 8th byte is name. Size off returns the overall size of the struct. Again, this is quite a good way to take a look at your struct's alignment. So because registered up front is 1 byte and name is 16, registered is then padded with 7 bytes, resulting in the total of this struct being 48 bytes. If we organize this struct correctly, like so, use 16, 8, and then do proper alignment, we can fit far more fields in this and actually have the struct smaller in memory, and size off shows us this. Alignment off just shows the alignment value of a given type. It's not really worth showing. So what about these functions are unsafe? If I'm going to be honest with you, not much. And Rob Pike has even has an open proposal on the Golang project to move these functions to another package in Go 2. We just can't do it now because of the backward compatibility promise. The real lunacy begins when you start using unsafe pointer. So what is an unsafe pointer? As seen before, the standard library defines this as a pointer of an arbitrary type. This is it does look a bit unusual, but it just means that we're pointing to a memory address without any type assumptions. To understand this, we'll first look at a typed pointer. If we have a pointer to an integer that points to some memory address ending in 158, Golang isn't just concerned with this memory address. It is instead concerned with 8 memory addresses starting with that pointer. So if I have I to be 34562, and then I dereference I get the memory address of it, I will then point to this memory address, but whenever I dereference I, it will read up until this memory address. If we have a string or a pointer to a string, Golang isn't just concerned with that memory address, it's instead concerned with 16 memory addresses starting here, and it will read right up until 167. You might notice, holy hell, multiplied by 42, that's like a length of like 300, but we're only getting 16 bytes. We'll get into that later. If we convert a typed pointer to an unsafe pointer, we're pretty much pointing to just that single memory address until later down the line. So if I make I become equal 34562, and then I cast it to an unsafe pointer, what I will point to is what you'd expect, the memory address, and then 8 after. What P points to is just this. This is all it cares about for the time being. This will remain the case until we read the unsafe pointer as a type, and herein lies the madness. So with this unsafe pointer, we can have binary data stored at I, a pointer to I, be read as another type. To dereference an unsafe pointer, we first cast it to a type, and then the data is read as it would be for that cast, for that type. So ignore this madness there for the stir equals. We'll get into that there shortly. But continuing from the previous example, using the unsafe pointer as a medium, we can have I point to this memory address, and then whenever we reference I, it will only read to here. But we can then wrangle this unsafe pointer into a string, and whenever we read from the string, it will read to here, some completely undefined point in memory. So like, what the actual fuck is that there? So let's just break this down, right? So we start with I. We dereference I. We cast I to an unsafe pointer. We then cast that pointer to a pointer of a string, and then we dereference that string. So you just wrangle it to a pointer to whatever type you want, and then you just lift its value straight out. It's scarier. It looks scarier than it is. It's actually quite readable once you get used to seeing it. So why would we want to read a pointer to an int as a pointer to a string? Simple answer, we wouldn't. Don't ever do this. The uses of cross-type casting to improve performance applies to other data structures, and we'll get into that later. However, though, it can be very interesting to mess around with an unsafe pointer to see like how Golang reads data under the hood. So if I take this lovely way, this example here, we create a new integer for I, so a pointer to an int64. We will then, using an unsafe pointer, turn that into a Boolean, a float, and an array of 8 bytes. And then if we do func to println for B, it will return false. Why is that? Because I, B, F, and A are all pointing to the one memory address. I, F, and A will read 8 forward, but B will only read to the start. So whenever I'm about to write to this, we will see 4 different variables, 4 different types competing for the same data to see how they'll read it. So let's say I write 10 to this integer I. You can see from the outputs here, the Boolean will now come out as true. The float will come out as some incredibly small number, and the byte slice just shows how it looks in bytes. So if I show here, I points to B points to F, A points to this, we have this data stored in this memory address. Whenever B reads that, it's like, oh, this isn't 0. That's sweet, and comes out as true. Whenever the float reads it, I'm assuming Golang kind of does things with the IEEE standard. So whatever the mantissa multiplication of this, converting it into, whenever you read it out as an integer, whatever the multiplication results in, we end up with an incredibly small number, which is why it isn't 10. If we write 256 to this memory address, you'll see the Boolean now reports itself as false. The float is now a slightly smaller, but still, slightly larger, but still incredibly small number. On the output, you can see from the array is 0, 1. So Golang stores integers in a little endian fashion, which results in the address that B is pointing to being zeroed, so it reports itself as false. Then whenever it goes to read the integer, it will put this 1 in front, and that gets you 256, and the rest all perform as you would expect. And finally, we're going to write a negative number to this. And I'm sorry to ruin Golang for you folks, but Golang has nan. If you write -10 to this memory address, it becomes uncomputable for a float to read, and it just reports itself as none. So again, this is how the data looks under the hood. Yeah. We also have this concept of a UN pointer. So a UN pointer is an integer representation of a memory address. You have a memory address via an unsafe pointer. You can cast it to an integer, and you can start doing pointer arithmetic on this to like add and subtract from memory addresses. This is insane. Like, so, but like, so just a heads up. Like, so we have this I is like a new int. So we instantiate it in memory. We write 256 to it. We cast it in an unsafe pointer. And you can see after hexadecimal to decimal, we get this value. We can do I++, and then it ends, instead of ending in 48, it ends in 49. And then we can read that there as a byte, and that will get the second byte of I, which is 1. All right, so let's explain this real quick. We create our data in memory, all zeroed. We then write 256 of it in binary. We then instantiate this pointer as a UN pointer. We do pointer ++, it moves along. And then we read, and then we get our byte of 1. Never do this. Don't tell me what to do. No, seriously, pointer arithmetic and garbage collection is a really bad time. So take the following example bit of code here. We have a function that returns an integer privately, and I do this to force the integer to be allocated to the heap. In other words, it's now territory of the garbage collector. We then print out its memory address and its value. We then cast it to an unsafe pointer, but then also reference that there as a UN pointer. We then force an invocation of the garbage collector, and then we have defined 3 variables, 7, 8, 9. We then, where this pointer is, we will write -19 to it, and then we will print Q, P, Q, and S, so 7, 8, and 9. Right? What do we think the output of this program will be? This might take a couple of runs to show the faultiness, like, but let's see. Q has been overwritten by 19. Because Z has never been referenced again, actually, by anything, because like UN pointer is just an integer. It's not treated as a pointer, it's treated as an integer. The compiler and the garbage collector actually sees that there is done and it's free to be collected. So forcing the invocation does allow Z's old memory address to be reallocated, because if you can see here, they actually share the same memory address, and that happens to be given to Q. Whenever we write 8 to it, or whenever we write 19 to it, it goes and overwrites Q. If we run it a few times, we'll get that work there. You see -19 can jump about. It's completely random. So you can see how this is like, this can be quite dangerous. Okay, we get this is dangerous, but how can it boost performance? I came here under that pretense. Unsafe can boost performance in 2 main ways: avoiding allocations, meaning less garbage needs to be collected; avoiding data copying, meaning less CPU. Again, that sounds a bit too quick. In fact, this can turn a few like ON operations into O1, and there was a very, very small O, as we will see. Casts and slices. So while this is kind of less relevant in the world of generics, quite a bit of the standard library and third-party libraries don't use generics yet, so this does kind of matter. Let's say we have the following type, myCoolType, which is a string, and we want to pass a slice of this type to strings.join. Strings.join takes a slice of strings. How can we do this? Anyone know the answer? We can't do this. We can't just pass into strings.join. We get, you can't use myCoolType with a slice of strings. We can't even cast it. We can't cast it as a slice of strings here because, again, we get, cannot convert myCoolType to a type of slice of string, even though they're the same under the hood. We can't even use generics to kind of fill the type system because, again, it's like, oh, we can't convert this slice of T into slice of string, even though we have explicitly said in generics, oh, here, only this will only accept string types. The only real way to do this safely is to build a new map, a new slice of strings, and then copy the old data into that slice and then run that there through strings.join. At least the only way I know of. If I'm wrong, I apologize, but it'll keep my point going. We've all probably had to do something similar to this before, and we've all felt worried over how inefficient this could be when writing it, because you can actually feel it as you're typing it. You're like, what on earth am I doing here? So let's benchmark the safe approach. So I've wrote a quick benchmark just to show you. We have a sample of 5 using values from, we'll first do it with a slice length of 10, then 100, then 1,000, then 10,000, then 100,000 to see if performance degrades when using this. We have our test type of strings. We'll populate it with just hello. We will reset the benchmark. And then we will just do the safe conversion. So we'll make a new string, a new slice of strings, and then we will force every single one of those to a string. We then write the output to a global. This is just kind of a convenience in benchmarking. I don't think it would happen here, but sometimes your benchmarks can get highly optimized by the compiler to where they're actually not even testing anything. Code can be removed if it has no side effects. This forces the compiler to believe that there's a side effect. So let's run this and see. We'll run it for a maximum of 5 seconds. For anyone who doesn't know, benchmarks have 2 things, of a count and a timer value. Whatever is hit first, if it hits the number of times the benchmark should be ran, it'll end, or if it hits the timeout, it'll end. So just for a heads up for later on. So 10 is fine, 53 nanoseconds in operation. Is that good? Who knows? 1 allocation. You can see the performance gradually degrade, 100 to 1,000 to 10,000 to 100,000. Yeah, takes some time. Even though it's only 1 allocation, it's quite a hefty allocation as it gets in. And I know like a slice of like 100,000 isn't really that realistic to have to deal with probably, but 100 and 1,000, like they're not outside the realms of like possibility. So if you ever have to do copy one of these over, you're dealing with quite a hefty allocation and quite a hefty, like a non-trivial amount of CPU time dedicated to this one operation. The unsafe solution, we just convert the micro type to an unsafe pointer and then cast that directly to a string. And then we can pass that straight in. How does it perform in comparison? Same type of benchmark, same values, but the only difference is in the body. We do the unsafe pointer conversion. You ready? Immediate. It's ON. You get an immediate performance benefit. So all together now, just to run them in comparison, we're only going to run the previous ones for 2 seconds this time. Get this run away. And as you can see, there is 0 allocations on the unsafe approach as well. So this isn't even going to poke the garbage collector at all. We're flying. Why? What on earth? Like, why is this so much faster? So to understand this, we have to understand a couple of things. Well, a few things. The first is a string header. Second is how Golang converts to and from string types. The third is slice headers. So what happens when we convert a string to a custom type? So S is low, M is micro type through a typecast. Remember when we mentioned that a pointer to a string cares about only 16 memory addresses? Well, these 16 bytes is what makes up the string header. This means a pointer to a string doesn't actually point to the underlying data, in this case, hello, it points instead to this string header. So if I take a look at this one again, we have holy hell repeated 42 times. It points to these 16 memory addresses. The first 8 of these from here to here is known as the data pointer. If you took this binary and converted it to hexadecimal, it would point to another pointer elsewhere in memory where this actually holy hell data starts. The second set of 8 bytes is the length. So the data pointer tells you where to look, length tells you how long to look for. So this will come out something like 370 odd, whatever the length of this output string is. A struct representation of the string header, just for easier human understanding, exists in the reflect package. So we have a string header, which is a data uint pointer, and a length, which is an integer. The interaction of the string's content via string data is how Golang guarantees that when you add a string to your struct, it will only increase it by 16 bytes, despite the string being variable in length. So we have a string, holy hell. This creates this string header, data, OX, whatever here, length 9, and then that points to here. If we were to clone this via strings.clone, the underlying data would be cloned in memory, and the new string header pointing to this clone data is then created. So holy hell, and then my clone is strings.clone. That creates the following under the hood, my string pointing to here, and my clone pointing to here. It's here. However, if we cast my string to a custom type, the underlying data isn't cloned. Instead, we just get a new string header. That's created and is pointing to the same character array in memory. So here we have the string, holy hell. My cool type is a cast of that. And under the hood, that looks like this. We now have two completely separate string headers, but they're both pointing behind the scenes to this under n slice of bytes. So for every iteration or loop, we're cloning 16 bytes of data. The combination of the allocation from string make string len of because whenever you create a new slice in Go, if you do not give it a constant, if you give it a variable bit of data, Go cannot guarantee that that will be a small enough slice to fit on the stack, so it allocates it to the heap out of safety. So the allocation from this, iterating over every item and making a copy of a string header for each item all adds up to the degrading ON execution time. Why is Unsafe faster? Because it takes advantage of the fact that there's no real difference between a slice of a type and a slice of a custom type that's backed by that type. If we take a look at the Unsafe solution again, this casting an entire slice from one type to another, how is this possible? Because we're not actually casting the slice, we're casting the slice header. So a slice header is like a string header, only they're 24 bytes long. The extra 8 bytes determine the slice's capacity. So here we have BB, the first 8's the data pointer again, so where that slice is in memory. The length is the length that we're currently pretending the slice is. And the third set of 8 bytes is the capacity, so the actual length that is reserved for the underlying array. Likewise, we have a struct representation of this, data UN pointer, len int, and capacity int. So with the following, we have a slice of Michael type. We force that there conversion to a string via unsafe. This does 0 duplication of data. Instead, we create SS and have it point to the exact same header as MM. And this is how it looks. So instead of the duplication, both of them coming in, we're just the same thing. If you ever reference SS or any element in SS, it will treat it as a string. If you ever access any element in MM, Golang will treat it as if it was that type. So we have access to the receiver functions again. Any questions so far?
So when you're casting between those, you have a custom type with some functions on it, will they still work?
They will work on the custom type. They won't work on the string. Okay. You're just all the type does is tell Golang how to access the data stored here.
Okay. Okay.
Sweet. Continue on. Casting a slice of bytes to a string. So this is probably so the previous one, like all in all, like in terms of like how dangerous is this one? Sorry, I'm not too sure. It's definitely, I feel like it's the safest out of all the things I'm going to show you today, but it's still not safe because you're using unsafe. Because like the danger is if you go and change the underlying type of, let's say, my cool type to be an integer, the compiler will help you throughout your entire code base to say, oh, here, this is meant to be an int, this is meant to be an int, but it will not help you with this unsafe conversion. It's up to you to find this out at runtime. This is whenever your program just starts randomly down. So yeah, casting the slice of bytes to a string. Golang by design doesn't have many built-in operations that are ON, as this can lead to writing expensive code without even realizing. We've all seen Python one-liners that are fucking horrendous in terms of execution time because innocuous function calls like sum or any, like they're doing full list traversals without even realizing. Casting a slice of bytes to a string and vice versa is one of the few exceptions. Given that a string in Golang is immutable, but a byte slice isn't, in order to ensure integrity, converting a string to a slice of bytes makes a full clone of the slice of bytes. So we have this slice of bytes, we cast it to a string, we change the first byte in the slice of bytes to a Z, and then we print it out, but the string is unscathed. So I probably don't need to go through this, but we create BB in memory. We then completely clone it for S. And for the next one, you'll notice this value here will change because it's set to the Z. And then it's printed out and we still get hello world all safely. I'm sure you can guess this clone isn't cheap. Yeah. So benchmarking the safe approach. So again, we do a similar thing, only we've added another sample of 1 because I kind of want to compare what it's like to copy 1 byte of data compared to doing this the unsafe way, just out of interest. So we just define our bytes repeat the 1 byte for however long the test is. So the 1, 10, 100. We reset the timer to ensure that this doesn't actually factor into our benchmarks. We then force the conversion to a string and then do the wee compiler trick to not have go inline any of this. Let's run it again. So the first one, 2 nanoseconds in operation, no allocations. The rest of them will allocate. I think the reason why the first one doesn't allocate is because bytes.repeat might have like a wee handler if in it to guard against if you only pass in the number 1. So the performance is degrading, but it's not degrading at a rate close to what was seen before, but it still is getting gradually worse. We've only seen 1 10x degradation as well. But yeah, so it caps out at 100,000 bytes. It takes 88,130 nanoseconds in operation. And that actually isn't completely unreasonable as opposed to the last one. You can have received some massive amount of data from like a web request and cast that to a string, and all of a sudden you're tanking your own memory. So the unsafe way is to just cast it to a pointer to a string, the same way you'd expect before. Oh, sorry, yes, sorry. Didn't even read my own slide there. Truth be told, there are 3 ways to do this. You cast it to a string, as you would a pointer to a string. You call the golang helper functions we've seen before, which we will get into, don't worry. And you cast, instead of casting the entire type, you cast the string and the bytes to the actual struct representations of their headers, and then you just overwrite the data. So again, we'll explain all this better. So, but first off, before I go down, can I explain this? I do, yeah, that's right. Sorry. So before we get into the explanation, I'm just going to benchmark all 3 approaches so you can see what they're all like. So first one is a direct string cast, as seen here. Let's go. That was one of the fastest operations I've ever seen in my life. It's actually when I first wrote this and ran it, I actually had to have a print out global afterwards to make sure this just wasn't like getting optimized the way it isn't. It actually is doing the cast, because like that's like 0.2 is not even a clock cycle. Next one is the unsafe helper functions. Slightly slower, but again, if it's that constant, like who's going to care about the 0.2 nanoseconds? And then the final one with the slice header casting. Again, slightly slower again. But again, if any of my functions could consistently run at less than a nanosecond, I'll be buzzing about that too. If you pick one of these, if you're going to do this at all and you pick one over the other 2 based on execution time, like no, like all 3 together, just because they're so quick, I have no issue running them. So we'll do the string cast first, the actual safe way of doing it. That is expensive.
Is there one of these that you think is safer, or are they going to?
I'm getting into that. That will come.
Oh,
the question there was, there's the one of them I think safer. There is one that's safer, but none of them are safe. Like that's, I do not want to at all give that impression. If you ever do this, you're already off the beaten path. So, right. So the direct cast, how does this work? Similar to casting over a custom list, we create a var s and tell it to read the slice of bytes data, but as a string. There is, however, one interesting quirk here. We're casting a slice to a string and thus casting the slice header, which is 24 bytes, to the string header, which is 16. This results in the final 8 bytes of the slice header, the capacity, being ignored by our new string. This doesn't actually matter, though. I don't know if this was a deliberate choice or a happy coincidence, but because the first 16 bytes relate to the same thing for both strings and slices, it's fine. Well, fine. So here we are. So BB starts here, BB ends here, but S, while starting here, ends here. Simple. This is mostly fine. The unsafe helper method approach. So yeah, Unsafe slice data takes a slice and returns a pointer to the starting element of that slice. It's calculated by reslicing the array and returning the first value of it. For some reason, I don't know why it does that. The Go implementers are smarter than I am. So here you provided the struct, you provided BB, and it will return a pointer to where 72 is in memory. Its functionality is similar to just passing in ampersand BB0, so getting the first address directly, but it has a couple of safety checks around nil. So I would recommend you use that. Unsafe string takes a pointer and the length. It will then build a new string header with the provided pointer being used for string header.data and the length as string header.len. So here you're literally saying, create me a new string, just to fucking build it out of nowhere. Here's the pointer where to start, and here's how long it has to be read for. So the result of this is, you have both your bytes, your slice of bytes, and your string pointing to the same backend array in memory. Now, obviously, this breaks string immutability. If you modify this slice of bytes in any way, shape, or form, it will modify the string. And that's where the strings are meant to be immutable. That is where the breaking integrity lies. Manually creating the header. So let's go through this line by line because it's kind of interesting. We created a slice of bytes. We then create a zeroed string. This creates a zeroed string header with its data pointer as 0 and its length as 0. We then cast the pointer to the string to a pointer to the string header. So we get back the 0 data in a wee struct, and then we do the same thing for the slice of bytes. Only it's not zeroed. We'll be able to access data and length directly. We then set the header, the data in the string header to match the data in the byte slice header. So data is now the same. So the string will now point to here in memory, but it has a length of 0, so it's not going to read forward at all. It's pointing somewhere, but it's got nowhere to go. We then set the length to match, and voila, we now have a duplicated string. We now have a string pointing at this slice of bytes.
Quick question there. Sorry, see if you added a print between the s header dot data and the s header dot length. What is the output? Nothing, or is it output h?
Oh, so the question was if I added a print between s header dot data and s header dot length. So in other words, if I in between these two lines printed out what s was, what would it be? It would be an empty string, because we can point the string somewhere and it can be length 0. It's not going to read forward. So if I set the length to 1, it would then print h. So what should these use? What should they use? Off them all, I think the safest is the third method, just strictly because we have significant more control over the cast and we build it ourselves. More lines is better, in my opinion. However, we could probably take inspiration from the standard library here. Here's the code for strings.clone as of Go version 123. It checks if the string is 0 in length and returns an empty string. Otherwise, it clones it straight into a slice of bytes and then does an unsafe string cast doing the direct access method. So it's not even using the wee helper function there. The reason clone does this is because, it breaks string immutability, but this back and slice it can never actually be accessed outside of the scope of this function. So it's completely fine to do here. So more of the story, we're already far off the beaten track, so who cares? So casting a string back to the slice of bytes, it's largely similar to a slice of bytes to a string, but there's one massive difference. One of the methods is invalid, and while creating code that will execute is very dangerous, bordering on actually it is completely undefined. Does anyone have a guess at which one of these methods should not be done? Apart from all three, but if you had to pick the worst one.
So the first one is the header.
Yeah.
Messed up.
Yeah, that's exactly it. That's exactly it. The first one, and our winner is this. The reason being those pesky headers again. You've only heard about them and you're already hating them. So once again, a string header is 16 bytes, a slice header is 24 bytes. If we cast a string header to a slice header, our read will overshoot by the allocated 8 bytes that are dedicated to that string, and it will read random data into the slice's capacity. So string starts here, string ends here, but then BB overshoots into Lord knows what. And this can lead into all sorts of chaos, undefined behavior, to memory leaks, to corruption, because if this happens to be a massive number, right? If this capacity happens to be some random data that just forms some massive integer, well, then the slice that this is pointing at will now be deemed from there, this massive amount of data forward will be deemed allocated in terms of the garbage collector because BB is pointing at it. So this memory will never be reallocated. It also means that if this data overshoots into like some other struct writes to it rightfully, it will modify our slice's capacity too. So any questions so far before I get into the third and final finale of this? Nope. Sweet. So avoiding allocations. One of the sad parts of Go for me is balancing these three facts. Interfaces are awesome and allow for easy mocking. Allocating memory to the heap is very expensive. Passing a pointer to an interface always allocates. So if you want to write an easily mockable service, we have to accept we'll be poking the garbage collector somewhere. It's just a fact of life. So why does it allocate? So from the compiler's point of view, it's very simple. Let's say you have this interface, a relayer that does a relay of a message. And you call this relay function. So we pass the relayer in and we just call relayer to the pointer to the message. We have actually no idea what the concrete implementation of the relayer is going to do to the message. It might save the message. So we have photographic memory one, I can't even pronounce that. Every message gets in, gets saved. It could fire it down a channel to be used Lord knows where. Or it could fire it off in the Go routine. We can have a compile time, no. And because the compiler cannot guarantee that this pointer, the data that this struct is pointing to, it cannot guarantee that it won't live longer than or remain inside the scope of the interface's function. It moves it to the heap. Can anything be done about this? Yeah, you don't want to, but yeah, though you should probably never do this. So take the following very, very contrived code. We have a service that handles person entities. Again, this I can't stress. This was written yesterday in the space like 2 hours. So this is completely an unrealistic example, but it gets the point across, I think. The service will call a repo, and the repo saves the person entity to a store. So we have person service, we have person repo with our get function and our store function. Then we have a half-assed attempt at a generic store that has a get, and it just takes that type in, and the key is always an integer, and it has a set, and then you can set that out. So get, notice deliberately, because this is contrived, doesn't return the value, it instead takes an out pointer, so it'll obviously overwrite that there. The implementation of this store uses a map in a non-thread safe way because demo. So you just, whenever you get, you just write over the top of it. Whenever you store, you just store it in. So we implement the repo and service as you'd expect. So the repo is just called store.get on the ID person, and then for the actual store of it, you just set the person with their ID. Then this is a service as well, just relays calls directly to person. So let's just run a quick benchmark in this, right? So we're first going to test person, so retrieving the person from this stupid store, and then we're going to test setting a person. So we're running. So nothing too bad, and again, you're not going to see mad performance gains here, just not to spoil anything, but like notice there's 2 allocations. And there's 1 allocation on setting it. So out of curiosity, does anyone, if I had the code up, it would actually be better doing this. The allocations come from this args being passed as a pointer, and this out variable being passed as a pointer as well. There's 2 allocations in the get, but because the store doesn't actually have a out pointer, this person's covered by the previous allocation Alera. So the unsafe way to do this I have the exact same repo and service interfaces implemented in an unsafe way. First, we'll look at the benchmarks, then some background, then we'll show you the code because again, you're not going to see mad performance gains. The previous one was like 44 nanoseconds and I think 300 nanoseconds on up. This one, 14 nanoseconds with 0 allocations. And the other one, I've actually seen it run slower, but we get 0 allocations, but we'll see. Yeah, 300 again, but again, 0 allocations. I think most, like, saving 1 allocation saves you no time, and the hashing of the integer into the hash map is actually just taking up all the CPU time, so it's a bit variable. But we cleared all the allocations, so we can feel good. That's neat. But how far from God's light must we stray for the very? So for this, we leverage 2 compiler directives, the first being go no escape. Go no escape must be placed. It's a compiler directive that has to be placed before a function is declared. And it disables escape analysis on a function's parameters and return values, meaning any pointers passed in will not leak to the heap. There is, however, a catch straight from the docs. The go no escape directive must be followed by a function without a body, meaning that the function has been implemented. The function implementation has not been written in Go. So for example, we get go no escape hello, go no escape goodbye. So like, okay, this is cool, but unless we're willing to like link our code with C, like this is pointless, like who cares? Like, but then there's also this one go link name. This directive is pretty cool, but like all cool things, you can only use it if you import unsafe, because it completely ignores the type system and actually breaks modularity. So this lets us stub the body of one function out with another. So let's say we have the following function, just some stupid thing, positive rand. It gets a random integer and then returns a between 0 and I. So if you pass an 8, you get something from 0 to 7, and then it returns the positive result of this calculation. There's a reason I didn't use math at absolute, because go link name doesn't let your code compile if for whatever reason. But yeah, so we have random integer, give me something between 0 and 7. We have the following test, 2 util.positive rand 7, and in this test we always wanted to have 2. We want to assert 2 is equal to the output. How can we do this? Well, one way is just to seed the random like a seeing human being, but we are not seeing people here. You can use go link name to actually stub the body of the function. So what you say here is you're telling the compiler with this go link name, take this function, and this can be a river, but always declared above, and actually slap it over the top of this function at compile time. And there your math.roundInt is now replaced with return 9. What? So another use of this is using time.sleep as an example. So has anyone here ever gotten curious and looked at the implementation of time.sleep in the standard library? I'm going to show you it. Body was completely underwhelming. Like, yeah, actually, you might think to yourself, oh, this is just doing some mad stuff under the hood and C or something, Lord knows, like, you know, they just couldn't write this and go. Well, it turns out not. If you do a bit more digging in the runtime package, there's this unexported function called time sleep with the go link name above it. So we take the body of this time sleep function and are slapping it over the top of a function in a completely different module. So our unexported function is now callable from the time package. Why would they do this? I think runtime.sleep might have made it sound like you're pausing all Go routines instead of just the one calling it, and important runtime just to call it sleep seemed a bit weird. I'm sure they had the reasons. But time sleep is no body, and go link name lets us stub the body in. Can you kind of see where this is going when you think about it? This stubbing of an empty body with the previous directives we had. So bringing it all together, even though go no escape forces us to create a bodiless function, it doesn't forbid the body of that function to be stubbed with go link name. So let's look at our unsafe implementations for this very small person service again. Unsafely done. So we have our person implementation that calls this under person. Now, why have I went under? If you're doing this, you're already so far off the beaten track of like Go. Who cares if it's right? They're like write it as if it's like Python or JavaScript, something trying to like imply some sort of like visual privateness. It calls this anyway under person. We have store person that calls under store person. We then have a go no escaped and a go link named function on our person, and this is bodiless. The go link name links this under person to service impl person, and that has the body. So we pass the repo in that is on the struct as an attribute into this function, and then we call repo.person. and that disables the yeah, it's horrendous. Like that disables the runtime, the compile time escape analysis check, and completely avoids the allocation. The same thing's done with store person. We link the body of store person into under impl under store person, and do the same. And then same with the repo layer, largely similar. We have under get, which is just under get, impl get, store get, disabling escape analysis, no longer goes to the heap. And yeah, that's it. Like, so one thing I'll say quickly before this is that when you do this, you get no help from the compiler that the arguments in here are the same as the arguments in here. You can pass in different data, and kind of similar to how if we read the float as an integer from before, that's how we will receive that data. If you have an int going in one end and you receive it as a float in the linked function, it could come out nan for all we know. So you're gonna wanna, if you do this, don't. But if you do, you're gonna wanna have the bodiless and the body right beside each other. And yeah, that's it. So my sources for this have been go101.org. If you don't know it, it is a fantastic website that gets really low level on Golang, and they have a fantastic article on safe and memory allocation. There's also oh god, okay. There's also the other source was the Golang standard library. This actually started as I was reading the strings package and came across strings.clone and was like, oh, here, that's kind of cool, like Unsafe, what? And then, yeah, that's it. My GitHub is chai latte. So thank you all. Any more questions before I go?
I mean, you mentioned at the start, there was stuff about like headers and memory being in certain places, right? So does the order of the fields in the struct matter?
Yes, they absolutely matter. So if I can show you here, so the question there was, did the order of the fields in the struct matter to the in-memory representation? Yes, it absolutely does. So if I can get this up again, where are we? So the way this is, this anonymous struct will be laid out here is registered is the first byte in that struct. Then we get, whenever you go to read most values in Go, the value can only exist on a memory address that is divisible by the size of that struct. So if something's 8 bytes long, it will only exist in the memory address that can be cleanly divided by 8. So we have something that is 1 byte, and then we have something that is 16. Go has to do some padding to pad this 1 to 7. So the first byte will be 1, the next will be a load of just like empty like nonsense, and then we'll eventually hit name. That's why in this struct here with few fields is 48 bytes long, as is the output, but this next one with far more fields is 32 bytes long, because we're actually doing proper alignment.
Right.
That makes sense?
Yeah, that makes sense.
Sweet.